Okay, now that we discussed how to find the context vector we were for input token 2, let's put everything together now. So we are going to create this self-attention v1, which is version 1, and we're inheriting the module, the module from touch. The reason is because we want to get this parameter and we just initialize our WQ, WK, WV. So this is the class that we're going to use. So the reason why we're creating as a class here is because we want to take it, we want to use it again in the future. So in the future, when we are now doing the actual training, I think in the next chapter, when we get into deep dive of training, we will need a class to really make it easier. So that's why we're just creating a class here. In the forward pass, we calculate our keys, calculate our keys, and now we're doing for all inputs. So it's just going to be the X for all inputs, queries. So this will behave the query number one, number two, number three, number four for all inputs. So it's X, of course, matrix multiplied by the query matrix, and then the values, which is just your X, your inputs, multiplied your X that will pass here, multiplied matrix multiplied by your value matrix. That's it. So now we have our KQV. And then we calculate our attention scores by using those queries times the keys. Here we're just transposing and would have calculated our omegas or those W ones. These are the attention scores. Attention weights will then do this, and these will be our alphas, right? Those will be our alphas. So we will, now we are scaling. We're scaling using the soft max, which is our attention scores. And here we are just getting the dimension of the keys, which is the last dimension, which is the embedding dimension square root. That's all we are doing here. Perfect. And then dimension, and then we are doing it by the last dimension, right? Scaling, we have our weights. Now that we have our weights, we apply the values. We do the matrix multiplication with the value vectors to get our context vectors. And now we have our context vectors. That's essentially it. That's it right there. That is the scale dot self attention dot product self attention. Here we test it out because we have our inputs, right? We have our inputs from previous chapter. We then just apply this class. Let's see what happens. These are the results. These are the results we get. But we can do it much better, right? We can change from NN parameter to NN linear. Because NN linear, it is preferred weight initialization scheme, which is more stable for during our training. So let's change that. So we'll create our self-attention V2. And we are going to use NN linear instead of NN parameter. But the linear model comes with bias. It comes with bias. If you've done neural networks before, you know that your weights will come with a bias term. Here we are going to say bias equal to false. We do not want the bias term. We just want the weights and not, so each not okay, each layer of a neural network comes with bias terms. We do not want those terms. That's why we're saying bias equal to false. QKV bias, we do not need the bias here. So it's going to be bias equal to false. But essentially everything is the same. Essentially everything the same. It's a different initialization scheme. That's why the answers here, when we apply this V2 to our inputs, the answers are different. They're different, but the initializations, if you want, you can do same seed, whatever it is, you see slight differences there. So now that we have that, that's essentially what we wanted to show. Wanted to show now everything put together in one. So just to emphasize, let us just go to smooth draw for a few seconds. Let's go to for hopefully like a minute or something. So what did we try to do here? So what we try to do is just this. We have our inputs X. So this will be the embedding for X2. So this input X, we have all the embeddings that are ready now. We have 6 of them, embeddings for all the tokens. And we're initialized with the weight matrices. So weight matrix WQ, weight matrix WK, weight matrix WV. It will have an output equal to 2, but in GPT, the output will be equal to the embedding, which is 1000, well, 1000, sometimes 12,000, all of that. And our input is just going to be the input dimension, which is the dimension of the x itself. Again, in GPT, these are equal. Then what we do is we take that input and we apply the WK, the queries, and we get the queries matrix. We apply it on the K, we get the keys matrix. We apply the input X on the WV matrix, and we get the values matrix. So this now we have our KQV matrices. And we take the Q and the K matrix and we calculate this attention weight matrix. This has already been soft maxed. It has been soft maxed with the square divided by the square root of the dimension. So K and Q will now create the attention weight matrix. So now, your, this is, it's saying 0.19 attention to your, 0.16 attention to journey, and all of that kind of stuff. So this is the attention matrix, attention weight matrix. Then we'll apply the values matrix, because this is n equal to 6. And then this values matrix will have a 6 by 2. It'll be a 6 by 2. So 6 by 6 and a 6 by 2. When you do matrix multiplication, you get the results of a 6 by 2 matrix, right? 6 by 6, 6 by 2, result is a 6 by 2 matrix, which is 6 by 2, yes, 6 by 2, as you can see here. And those now, when you do the attention weights, matrix multiplied by the values, you get your context vectors. That's it. That's essentially what we did here. So now that we've done that, we are now getting into this. We're updating it again, this self-attention, but we're now going to get into causal attention. And causal attention, that's where we do masking. Let us see what masking is all about in the next video.